In this video, I'll be looking at the derivation of the points of inflection for a normal distribution curve. Just by way of recap, we're going to review the three types of skew that may be present within our data set. So for the normal distribution, if the data is can be modeled by a normal distribution, we would expect that the skew will be zero, i.e. that the mean will equal to the median, which will equal to the mode. The positively skewed data means that most of the values occur early on and a few occur later on. We would expect, for example, that within a particular economy, income is distributed or has a positive skew. So what that means, we would expect that the majority of folks have low income to medium income, while very few individuals have high income. Within a classroom, ideally, every teacher would like the skew to be negatively skewed. What that means is that we would like for most of our learners to be high ability, but a few of the learners will be low ability or low performing in that particular class context. So for today's, the main aim of today's presentation will be, as I said before, the derivation of the x coordinates of the inflection point on your normal distribution curve. This is not required generally by the exam boards, but doing so will flesh out some of the skills that you would have been taught from the pure modules, and will allow you to see differentiation and apply to the context of statistics. All right, so our first step will be to state or to identify what is the normal distribution function, or the probability density function for the normal distribution. So f of x is equal to 1 over sigma times square root of 2 pi times e to the minus a half x minus mu over sigma all square. So we want to differentiate this, and we recall from our differentiation module that when we are differentiating an exponential function, we can follow the following rule. So we know that if y is equal to e to the g of x, then dy dx is equal to g dash x e to the g of x. So in order to differentiate this function and applying that rule, we simply differentiate the power and then multiply the original function by the derivative of the power. So we can differentiate the power using the chain rule, and when we differentiate this, we're going to get f dash x to be equal to the derivative of this. We multiply minus a half by 2. So that's the differentiation of the outside. And then now we multiply by the differentiation of the inside, which is 1 over sigma. So we will have minus a half times 2 times 1 over sigma, and then times by the x minus mu over sigma, and then multiply that now by original f of x. So we can write it like that. So that is our first derivative. Now, in order to get the inflection point, again, recall that a condition for the inflection point is that d square y dx square must equal to 0. So this is what we would call a necessary but not sufficient condition. What that means is that even though d square y dx square may be 0, it does not imply that we have found an inflection point. We may have found an inflection point, but it is not necessarily an inflection point. So do be aware of that subtle distinction. So continuing, we're going to now differentiate the first derivative and get the second derivative. So in order to differentiate this, we have a product. We're going to use the product rule. So by way of a refresher, the product rule states that if we have a function y equal uv, then dy dx is equal to u dash v plus v dash u. So we're going to apply this rule. So we're going to treat this as our u and then treat this as our v. So f double dash x will be equal to, differentiate this term, we're going to get, this simplifies to minus 1 over theta, and then times the differentiation of this. So that will be minus 1 over theta times, when we differentiate this, we get 1 over theta times f of x. So minus 1 over theta is the simplification of minus a half times 2 times 1 over theta. And then when we differentiate this, x minus mu over theta, that is similar to x over theta minus mu over theta, differentiating that. We know that this will differentiate to 1 over theta, that will differentiate to 0, and hence we are left with 1 over theta. Now the second part of our rule states that we must now differentiate v dash. So we'll get f dash x, we must differentiate v, sorry, and get f dash x, and then multiply that by u. So we're going to have f dash x multiplied by u, which is going to be all of this. So that's going to be minus 1 over theta times x minus u over theta. And all of this must now be set equal to 0. So for the time being, it is easier to write f of x and f dash x. Since we know clearly what f of x is, we know what f dash x is. So if we need to substitute, we can do that. But it just makes it a little bit more economical in terms of the writing out if we keep them as is. So let's apply the condition for the inflection point, which is to rearrange for x when all of this is equal to 0. So what must be true for all of this to be equal to 0? Ideally, we want to write this in factored form and then solve for x. So we're going to now substitute the expression for f of x. We're going to substitute the expression for f dash x and see if we can factorize from there. So this will be equal to minus 1 over sigma square times f of x, which is 1 over sigma root 2 pi e to the minus a half x minus mu over sigma all square, plus f dash x, which is all of this. So that's going to be minus 1 over sigma times x minus mu over sigma times f of x, which is 1 over sigma root 2 pi times e to the minus a half x minus mu over sigma all square, now multiplied by that expression times minus 1 over sigma x minus mu over sigma, and all of that must be set equal to 0. So at this point, what we'll be looking for is an opportunity to simplify where possible. Notice that e to the minus a half x minus mu over sigma all square is common to this arm of the expression as well as this arm of the expression. So we can cancel here and we can cancel there. Notice as well that 1 over sigma root 2 pi is also common to this as well as to that. So we could cancel there and we could cancel there. All right, so let's look at what we have. we have a minus 1 over sigma square, and we have a minus 1 over sigma square as well. So we could further cancel. That would go to 0. That would go to 0 with that expression as well. So what are we left with at present? So we have, this is equal to 1, then minus 1 over sigma times x minus mu over sigma. So 1 minus x minus mu over sigma square, and then we also have a x minus mu here. So that will be square equals 0. Rearranging and multiplying, so we can multiply through by sigma square on both sides. This implies that sigma square is equal to x minus mu all square. And from here, we can take the square root of both sides. So continuing. So x minus mu all square is equal to sigma square. Taking the square root of both sides, we have x minus mu is equal to plus or minus sigma. Therefore, x is equal to mu plus or minus sigma. And there ends the derivation of the x coordinate of the turning point. So we have x1 to be equal to mu minus sigma, and x2 to be equal to mu plus sigma.